Hello, dear students. Welcome to the Quantum Group. Here is a question number 3.23 of Irodov. Question states, an infinitely long cylindrical surface of circular cross-section is uniformly charged lengthwise with a surface density sigma is equal to sigma naught cos phi, where phi is the polar angle of the cylindrical coordinate system, whose z-axis coincides with the axis of the given surface. Find the magnitude and direction of the electric field strength vector on the z-axis. So this is a infinitely long cylindrical surface of a circular cross section. Suppose this is a cylinder of radius r, and let's take one section somewhere in between like this, and let's take some reference line from where we are going to measure the angle phi, and this is a reference line. From this reference line at an angle phi, this is a point, and at this angular position, it's written that the surface density, this circular cross section uniformly charged lengthwise. So along the lengthwise, along this length, at all points whose angular position is phi, like here is the angular position if I go here. So at this point, at all these points, the angular position is phi. All the angles are measured from this reference line, and at this angular position, surface charge density is sigma is equal to sigma naught cos phi. So how I am going to find the electric field at the center? So my plan is that I want to reduce this surface charge into the linear charge. So I will take a little length. Suppose I take an element between angular position phi to phi plus d phi, something like this. So at this angular position, I'm going to take this element of the cylindrical surface, and obviously this element will be a line element. So at this element, the charges would be like this. On this length, there would be charge, and the thickness of this line is r d phi. If this is r, radius is r, this elemental angle is d phi. So this thickness is r d phi. And suppose if I have a direct formula to convert this sigma into lambda, but I can give a little proof also. So I'm taking a very small length, say this length dl of this elemental wire. So the area, that this red shaded area, the area of this part would be obviously r d phi into dl. And suppose this little element has a charge dq. So dq can be written as a surface charge density into area sigma, and area is dl into r d phi. So at this position, in fact, at all these positions, at all these element, sigma is same. So now I want to convert this sigma into lambda, linear charge density, because now my element is this infinite var. So lambda would be obviously dq by dl. Lambda is dq by dl, and from here dq by dl would be sigma r d phi. And putting the value of sigma naught r cos phi, because the sigma varies at different angular positions. So that would be sigma naught cos phi r d phi. So what I will do, I will reduce all this surface charge to a linear charge like this, like this, like this. And now if I look the whole picture from the top, so I will find a picture looking something like this. From the top, I will find some infinite wire here, some infinite wire here, some infinite wire here, like that, like that, like that. So I'll be finding infinite wires, because I'm looking from the top. So I'm just seeing the cross section of that wire. So these cross section, through at these cross sections, there is a linear charge density lambda, and that linear charge density lambda is varying with phi. So at different angular position, there is a different linear charge density, and because of all these infinite wires, I have to find the electric field at the center. So let's see how the electric field is going to be. Let's go to the next page. So that top view of the cylinder would be like this. This cross are nothing but the infinite wires which I have reduced with a linear charge density at angular position phi to be sigma naught r cos phi d phi. So, and we have done this kind of question before, and this cos phi tells us that the charge density would be maximum here positive because phi is 0 here, and as I go from here to here or here to here, the charge density will decrease, and at these points 0, and from here to here it will be negative. So charge density would be something like this: positive, maximum positive, and slowly decreasing, coming to 0, slowly decreasing, coming to 0, negative, and here maximum negative, and like that. And so if you see that the pair wise, you can have some dipole combination here, dipole combination here, dipole combination here, dipole combination here. So because of this charge distribution, intuitively I can immediately say that electric field is going to be along this direction. Electric field will be in the direction where phi is pi. Along this x-axis phi is 0, along negative x-axis phi is pi. So now we want to exactly calculate the electric field. So I have at this angular position there is a infinite wire, and at this angular position the charge density is this lambda sigma naught r cos phi d phi. So because of this infinite wire, electric field will be along this direction. This is at a distance r, so that electric field will be 2k lambda by r. So because of the wire here, the electric field is supposed dE, and its x component will be dx, and the y component would be dEy. And intuitively I told you that the dex will add up and dEy will cancel, but you can see by integration also. So dE, because of the element here which has a charge density lambda is equal to sigma naught r cos phi d phi. So electric field, infinite wire at a distance r, 2k lambda by r, putting the value of lambda. So lambda is sigma naught r cos phi d phi. In place of lambda I put sigma naught r cos phi d phi. This r and r will get cancelled, so we will have 2k sigma naught cos phi d phi. And now the x component of this electric field, the x component of the electric field dex would be de cos phi. So d cos phi, put back the value of d here, so we are going to get 2k sigma naught cos phi into cos phi, cos square phi d phi, and I can make 2 cos square phi equal to 1 plus cos 2 phi. So that will become k sigma naught bracket 1 plus cos 2 phi into d phi. The bracket should be here. I think that's pretty clear. And similarly, the y component of the electric field will be, this y component would be dE sin phi. And dE, put back the value of d from here, 2k sigma naught cos phi d phi multiplied by sin phi. That's going to become 2k sigma naught sin phi cos phi d phi. And twice sin phi cos phi is sin 2 phi. So that would be k sigma naught sin 2 phi d phi. And now overall electric field along x direction, Ex is the integration of dEx. So for this thing, you can take k sigma naught outside, and within the integral, there is a 1 plus cos 2 phi d phi. So integration of 1 is 2 pi, integration of cos 2 phi is sin 2 phi by 2. You will put the value in limits from 0 to 2 pi, that sin 2 phi part will become 0. So overall we'll have k sigma naught into 2 pi. And y component of the electric field Ey will be integration of dEy, and dy from here, put back the value, take k sigma naught outside, sin 2 phi d phi from 0 to 2 pi. This integration will be minus cos 2 phi by 2, and on putting the limit, that is coming to be 0, as it was clear from the symmetry of the situation. So this component, y component, will come out to be 0. So overall electric field is going to be along negative x direction, and negative x direction is the direction at which phi is equal to pi. And net electric field is this, Ey is 0. So that is equal to Ex. Ex is equal to k sigma naught 2 pi. put back the value of k 1 over 4 pi epsilon naught. So we will get E naught is equal to sigma naught upon 2 epsilon naught. That is our answer. Thank you.